Hello again. Hopefully everybody is doing okay and not getting too bored being away from school. The last time that I did a little video for you, we were talking about exponential growth. And we're going to expand on that just a little bit today, talking about how exponential growth and money go together. Now, the picture you see a whole bunch of $100 bills, way more than I've ever had myself at any one time. But we're going to talk about how you can start with a little bit of money and get a lot of money using the magic of interest. Now, on a side note, I got a little bit of a laugh when I was searching for images to throw into this PowerPoint, and I came across this one of Ben Franklin, who was doing a bit of social distancing. So today we're going to talk about interest. And all interest is just money that's paid for the privilege of using someone else's money. Sometimes it's money that's paid to you because you give your money to a bank and they get to invest it in the meantime. Sometimes it's money you have to pay because you've taken someone else's money, like on a loan or a credit card. Either way, what happens is the original amount gets increased by a percentage, so eventually it grows into more money. There are actually two kinds of interest that we deal with. We're going to start with the easier of the two and then talk about the one that's far more common. The easier kind of interest is what's called simple interest. And it's the sort of thing that's used in just casual situations, like if you borrowed money from a friend or family member and you had to pay it back. Most of the time it's simple interest that's used in that kind of situation. The other big place where simple interest comes up is in the bond market, and it can also be used for some short-term loans. Banks and investment companies, though, rarely use simple interest, and the reason they don't is that they can make more money using compound interest, which is the other thing we'll talk about. The idea of simple interest is that interest ends up being paid only on the base amount of money, what we call the principal, the starting amount that you begin a loan with. The same amount of money or interest is paid each time. It never increases, it's always the same. Here's an example of how simple interest works. It says you have a $100 investment at 3% simple interest. You notice that after year one, you earn $3 in interest, 3% of 100, and so the total amount you have in that account is $103. Year two, you earn another $3, so you're up to $106. Year three, it's $3 again, and so forth. Every year, you earn 3% of that original $100. You get $3 more, so by the end of year five, we're up to $115. Goes up by the same amount every year. There's a couple of formulas that are sometimes used for simple interest. They're different from what we did with exponential growth earlier, but they involve some of the same variables. The first one says I, which it should make sense stands for interest. I equals PRT. And then I have one that either says A equals P plus I or A equals P plus PRT. So you might remember from before that P was always the starting amount. The P variable comes from the word principal, which is just the financial term for the amount you invest originally. And here it's saying you can find the interest by taking the principal times the rate times the time. And if I want to find the final amount, the accumulation, I take the principal plus the interest, or the principal plus principal times rate times time. So I equals PRT, and if you add that on to P, you get the final amount A. A typical problem might look something like this. It says you lend your brother $350. If he pays the loan back 2 years later, how much will he owe if you charge 5% interest? This is a real typical simple interest problem. You just want to know how much money are you going to get in the end, and you're going to plug into those formulas we just looked at. So again, the main formula was I equals PRT. So to find the interest, I took 350 that we originally loaned times 5%, which I put as a decimal, 0.05, times 2 years, and it's telling me that the interest is going to be $35. I add that on to the original loan, and what my brother's got to pay back is $385. Here's another quick example. An appliance store charges 4% simple interest on purchases that aren't paid immediately. Stores are another place that sometimes will use simple interest, mostly because it's easier for them to calculate. It says here, if you buy an $800 stove, how much interest will you owe if you pay for the purchase 6 months later? Now, I will tell you the thing that's a little bit of a trick in this problem is 6 months later. And that's because in financial problems, time always is given in years. So I need to realize that 6 months is actually half a year. And that's the number we're going to end up using for t. So the problem said 4% interest. That's why R is going to be 0.04. The stove cost $800 initially, and again, the time is half a year. So you can see to figure out the interest, what I did is I took 800 times 0.04 times 0.5 times a half, and I got $16. The question just said, how much interest do you owe? And so that's really the final answer to that question. Of course, what I've actually got to pay back is $816. And here's one more question with simple interest. It says a bond matures 20 years after it's purchased. If its value at maturity, so at the end, is $500, and the bond earned 2% interest annually, how much was the purchase price? This is exactly how the bond market works. You buy a bond that has a value printed on it, but you actually buy it for less than that face value. You buy it at what's called a discount, and only at the end of its term is it worth the amount that's printed there. And that's why in this problem, the variable we're trying to find is P. I know that A, the end amount, is going to be $500. I know the interest rate is 2%, so 0.02. And it says 20 years is the amount of time we're looking at. So I plug those numbers in here, and we need to actually solve that for P. And this becomes an algebra problem, which I've got worked out here. I multiplied 0.02 times 20, and I got 0.4. I put that together with 1p, which was the principal amount we'd have at the start. And basically, I get the equation 500 equals 1.4p. I divide 500 by 1.4, and it turns out we get $357.14. When you're working with financial problems, we pretty much round everything to 2 decimal places. That's because the financial world works in dollars and cents. You're going to always get answers that have decimals that go all the way across the screen of your calculator, but you want to round to dollars and cents. Now, simple interest is pretty straightforward, but it's really not used all that often. It does tend to be pretty casual things and the bond market where you use simple interest. And simple interest is not exponential growth. That's because it keeps going up by the same amount every period. If you remember that $3 that we kept earning on a $100 investment, it doesn't change. It's what we call linear growth, where it just goes up by the same amount one year after another after another. What is exponential growth, and also what's by far the most common kind of interest, is what's called compound interest. This is used by most financial institutions, and the idea behind it is that interest is paid both on the principal, both on that original amount that you invested, and this is the important part, also on interest that's already been earned. So not just that first part, but also on what you've already got in the bank. Here's that same $100 investment that we talked about earlier, earning 3% interest, but this time it's compound interest we're earning. And if you look through the second column, you'll notice that what's happening is that each year, the amount of interest I earn is more than it was the year before. Now on $100 and 3% interest, it's not that much different, but it always goes up. So the first year, I take 3% of 100, I earn $3, and I've got a total of $103. But the second year, instead of taking 3% of 100, I take 3% of 103. And because of that, I earn a little bit more money. I earn $3.09. The third year, I take 3% of 106.09. And each year, it's 3% of the previous amount. And since that amount's going up, the amount of interest I earn goes up as well. Now, in 5 years on $100, that's not a lot different, but we've already earned almost $1 more than what we had with simple interest. The key to compound interest is that each year you earn more interest than you did the year before. The same would actually be true on interest that you owe. If you, for instance, didn't pay off a loan or a credit card bill, each year the amount you owe is going to keep going up and up at an ever-increasing rate. Now, because of that ever-increasing rate, growth with compound interest is exponential. It's going to start off slow, but then it's going to rapidly get bigger and bigger and bigger. Here's the formula we use to compute compound interest, and all it is just a little more complicated version of the general growth formula that I showed you in the last video. The general growth formula said that you had A equals P times 1 plus R to the n. This time, what's in the parentheses and what's in the exponent is just a little more complicated. We have A equals P, 1 plus R over n, to the nt power. Now again, you're going to be given that formula anytime you need to use it, both in this class and honestly in the real world. There's easy access to that formula. What you do need to know is what goes where when you're working with it. So the variables a and p, which also came up back when we were doing just the regular growth formula, those come from the financial terms accumulation and principal. Principal, again, is just what you start with, like the amount of money you invest or how much a loan you take out is worth. And accumulation is just the end amount, how much your investment's going to be worth in the end, or how much you have to pay back on a loan. R is the rate of interest. And just like we did when you did the worksheet before, it's always a decimal. If it was 7%, you put 0.07. And T is the time, and something that's important when we are working with compound interest or financial problems in general is the time always is given in years. The other variable that comes up in that formula is N. And what N stands for is the number of times that your money is compounded per year. If you ever see like advertisements for banks, they will sometimes talk about their accounts and they will say like this account has money compounded daily or compounded quarterly or compounded monthly. They'll give you a number of times that that money is compounded per year. What that basically means is how many times do they actually do the math and credit your account with the interest that you've earned. The more often they do that, the more money you're going to end up making in the end. Some terms you sometimes see for compounding are annually, semi-annually, quarterly, monthly, weekly. They could actually do any amount that they wanted. Most of those, your common sense should tell you what those numbers are. Annually just means once a year, semi-annually is twice a year, quarterly 4 times, monthly 12, and there are 52 weeks in a year. These days, quarterly and monthly are probably the most common of those that are used, but in problems you could encounter any of those different amounts. The other common amount that comes up is compounded daily. And there you can actually have some different issues that can come up. Your common sense might tell you that there's 365 days in a year, and these days that is actually the number most banks use when they're doing compounded daily. Traditionally, though, they didn't use 365. What they actually used was 360. And there's actually a lot of financial situations where 360 is still the number that's used for daily. The reason why they went with 360 is that in math, 360 is a much easier number to work with than 365. 360 is divisible by almost every number. In fact, between 1 and 10, the only thing that doesn't go into 360 is 7. And since the compound interest formula has divided by n in it, it makes it a whole lot easier if you keep that an easy number. Sometimes they will actually use 366. You probably know this year's a leap year, so it kind of makes sense that there would be 366 days in the year. And these days, when you can program a computer to do pretty much anything you want, they sometimes will actually use 366.25, so it adds like a quarter of a day every year. When in doubt, use 365 if it does say daily, but I just want to have you prepared because especially if you take like an accounting class, you may find that 360 is actually the more common number to be used. I'm going to take a look at two quick problems with compound interest. The first one I just made up after watching the news this morning. Tells you families will supposedly get a $500 payment from the government for each child they have as an economic stimulus due to the coronavirus pandemic. And the problem says, suppose your parents let you invest your $500. You find an account that'll pay 6% interest compounded quarterly. How much money will you have 50 years from now? Like when it gets time for you to retire, how much money would you have just from that $500 that you start with? Setting this up just involves plugging the numbers in where they belong in the formula. So you start with $500, that's the P. The formula says 1 plus R over N. R is your rate of interest, and this problem said you had 6% interest. It's compounded quarterly, which means 4 times a year. And that 4 comes up not only on the bottom of the fraction, but also in the exponent. I take 4 times a year times 50 years. What's really going on there is they're paying you a fourth of that annual interest each of the times they compound. So that's why it's 0.06 over 4. But they pay you 4 times each year, which is why the exponent we take times 4. I just plug those numbers in and see what we get. Now, I know a lot of you don't have like graphing calculators at home, and that's why this example I just worked out in the calculator that's built into Google. And if you just do put scientific calculator into the search bar on Google, you come up with a screen that looks exactly like this. And you can type in this problem pretty much exactly like it looks. And what we'd say for our answer is $9,821.51. I actually worked this out two other ways. I did this on the graphing calculator that's built into my computer, and you can see that I got exactly that same answer. It really works exactly the same as when you do it with Google. If you have like an old, cheaper calculator at home, what you can do is work things out one step at a time. What I first did, because I'm thinking of order of operations, is I did what was inside the parentheses, 1 plus 0.06 divided by 4. So I just worked out those parentheses and came up with 1.015. And then I remembered that exponents come before multiplication. So I took those parentheses, that answer I just got, to the power of 200. All I did is in my head, I took 4 times 50 and I knew that was 200. And finally, I take that answer times the 500 that's out front, and you notice we get that exact same $9,821.51. So it doesn't really matter how you work it out, but you do get the same answer and you round to dollars and cents. This is a classic example of how compound interest works over time. We started with $500, which really isn't much money comparatively at all. And at the end, we have almost $10,000, which is a whole lot more money. If you talk to anyone that's like an investment advisor or anyone that works in finance, they'll always tell you that if you want to have money for retirement, you've got to invest when you're young. And that's exactly what's going on here. You take not much money when you're young, and while you couldn't retire on $9,800, it's a lot more money than when you started. Here's one other problem. It says a $10,000 investment earns 9% interest compounded daily. How much will it be worth in 15 years? Picture there is of a $10,000 bill that actually was printed by the United States back in the 1930s. We don't make $10,000 bills today. You may or may not know that the biggest bill you could get is a $100 bill these days. It used to be, though, that they would use high denomination bills to make transfers between banks. These days, that's all done electronically, which is why there's really no need for a bill that's worth 10,000 bucks, and all it would do would be inviting counterfeiters to try and make lots of money easily. But we're starting with $10,000. We want to know how much we'll have 15 years from now. And again, all we do is just crank out the formula. 10,000. And then I take 1 plus 0.09, 9% interest, divided by 365, which is daily. I take that to the power of 365 times 15. Something you do want to be careful of is the parentheses if you're working this out. Again, if you don't have a calculator that has parentheses that are easy to use, what you want to do instead is work out what's inside them, take them to the power, and then multiply times 10,000. We find out here that we almost quadruple our money in that time. We have an answer of $38,567.84. So for now, what we're going to do is just take numbers and plug them into that compound interest formula to figure out what that final amount ends up being. Where we'll go from here is to see how do you go about solving for other variables in the formula, especially how do you figure out what t is. That lets you answer questions like, when will you have $100 trillion? And since I chose to put this on the last screen, a lot of you have seen the $100 trillion bill that I have by the bulletin board in my room. And that is a genuine bill from the nation of Zimbabwe. But the reason it was printed is that the economy was so bad in Zimbabwe that 100 trillion Zimbabwe dollars was actually worth less than one US dollar. And so, yeah, it is a real bill, but it's really not worth anything. So you're going to be doing some problems that do involve working out interest, and I hope things go well with that. As always, if you got any questions, shoot me an email and we'll try and get you on the right track with things. Otherwise, have a good week and stay healthy.